Hello, myself Dakshaini C. Working as assistant professor, Government College Faroum, and I am going to discuss about the topic electrochemistry for the subject chemistry, paper physical chemistry. This session contains principle of potentiometric titration, acid-base titration, that is NaOH versus HCl, oxidation reduction reactions, potassium dichromate versus that is FAS, ferrous ammonium salt, and precipitation reaction KCl versus silver nitrate, complexometric reaction zinc sulfate versus potassium ferricyanide. Before we go for that is the potentiometric titration, let us know about the principle of potentiometric titration. So that is the one of the qualities by using potentiometer here. That here by the using the potentiometric titration, the titration can be determined accurately without making use of any visual indicator. So and also the potentiometric titration Nast equation according to which the potential of an electrode depending upon the activities of the reduced and oxidized form of the involved redox couple. We already knew about from the previous session, that is oxidized and reduced form, that will be a difference developed in at the electrodes, that you are going to find out the EMF of that cell. The variation in potential is gradual in the beginning but become faster as the equivalence point is reached. The variation is maximum at the equivalence point but become lesser and lesser behind the equivalence point. Thus, at the equivalence point, one observe a point of inflation. So when the once you know that that will be we are going to observe the inflation point in the potential curve. So where you are going to that you are going to observe the neutralization point which intersect the volume of the titrate. Before we are going to go for potentiometric titration, let us have to set up the potentiometer there. So that is whatever the potentiometer that should be standardized before using as an potentiometer for the potentiometric titration. So we are going to standardize by using any one of the standard cell here. That is usually that is a western cadmium cell used for as an standard cell because of it has some qualities such as uh, it is a very easily reproducible form of well-defined material made up of that one, chemically and physically stable over long period when it will be out of use, and also it is that will be a polarizable one. In addition to these, that is one of the essential qualities that its EMF should have a low temperature coefficient, and its EMF value at 20 degrees centigrade, that will be E is equal to 1.0183 volts. So which is connected to the potentiometer, then EMF to be examined. A selector switch connects the potentiometer separately for the standardization and the measurement setup. Nowadays, whatever the potentiometer, it is already standardized by that one. Just we switch that one and calibrate whether your potentiometer shows an EMF of that will be equal to 1.0183 volts. Yeah, by knowing the standard EMF of that standard cell, then we can calculate the EMF of the given cell by means of the Nernst relation. This is the schematic representation of the conducting a potentiometric titration here. So one must be that will be indicator electrode, another that will be a reference electrode. This is the volume, that is a titrate solutions, but is filled with the burette. Whatever the analyte that will be taken in the beaker And this is the electromagnetic stirrer, but it will be helps to mixing up of the solution. And this is the potential meter setup here. From using a potentiometer, first we are going to determine the neutralization point of that is acid base titration. This is one of the example for that, that is a neutralization reactions of that is sodium hydroxide versus HCl. This is we already knew from the common volumetric method how we are going to find out the neutralization reaction. Now we are going to, by using the potentiometer, you can detect the neutralization point by using a without adding any indicator. That is the one of the thing here. The acid base titration of an electrode whose potential depends upon the, because of it is an acid base titration, therefore it is depending on the H plus ion concentration. For the H plus ion concentration, we are going to use it as a hydrogen electrode, thin hydrogen electrode, or a glass electrode as an indicator electrode when you are going to place it in the HCl solution. If it is a hydrogen electrode, if it has your indicator electrode and which is connected to the reference electrode as an calomel electrode, then the galvanic cell that is represented by these equations, where how you already knew about in the previous session. So that is EMF of the cell that is measured by potentiometrically by using a Nernst relationship, which is equal to the, well, you are going to substitute the values of standard of the all those things, then you get 0.2422 plus 0.059 pH of the EMF of that cell. So procedure for that, take 100 ml of 0.1 molar HCl into 50 ml beaker, and it is to be titrated against one normal NaOH titration error, just like a normal volumetric analysis. 1 molar NO that is a titrate. The concentration of the titrate is usually always you are going to take 5 to 10 times higher than that of the solution to be titrated, so that the volume range is as small as possible. You must know about that will be a whatever it is, whenever the analyte solution titrated by the titrate, then you have to add by the volume range, that will be you have to keep 0.5 to or 0.2 to 0.5. So EMF of that cell would increase by 0.059 volts by every 10-fold decrease in the concentration of the H plus ion dot. One dot unit increase in the pH of the solutions. For example, initially that is a potential EMF that will be decreases. Therefore, by adding 9 ml in that, then only then there will be an increase in the 0.059 volts in the beginning. After the next you have to add a 0.9 ml, then although it will be the same thing. If I add another 0.09 ml of that one will also produce the same change, and so on. EMF of the cell changes slowly at the first, but more and more rapidly as the end point approaches. After the end point, further addition of NaOH produces a very little change in the H plus ion concentration. So here that is any one of the below potential curve which is to be determined the end point. Know that by using the table, that is the volume of added by 0.5 difference, and you have to mention that is the EMF of that one, and you have to notate that one, and what is the difference in the delta or a change in the volume and 1 by T and all those things. By using that calculations, then you have to plot whether that will be a typical potentiometric titration curve. You have to get an end point, or in a typical first derivative graph, or a typical of second derivative, or any one of a graph. From that you are going to determine the end point. So here, that is whatever that will be a year, that is from the common potentiometer, that is the a typical draw graph. Between that, you increase the accuracy of the equivalent sharpness. That's all. So whichever that is they can utilize for the determination of the endpoint or a neutralization point. Next, we go for the oxidation reduction reaction. That is a potassium dichromate versus ferrous ammonium sulfate. Here, what is the principle and the theory behind that? You already knew about that redox titration. It is a it one is the oxidizing agent, and it oxidizes to Fe, that will be in the Fe2 plus to Fe3 plus. So in acidic media, therefore we require a dilute sulfuric acid in that. So in the redox titration, it's also carried out potentiometrically. In this case, the electrode reversible concerning H plus ion, therefore it is replaced by an inert metal. Here inert metal we are going to use it such as platinum, where here it is immersed in the solution that contain both the oxidized and reduced form of the same species. That will be a platinum wire. We are going to use it as an indicator electrode. So indicator electrode, you are going to dip it in the, that is the oxidized and reduced form of, that is the iron solution. The electrode acts as a oxidation reduction electrode. That indicator electrode, that is acts as a oxidation reduction electrode. That's the oxidized form. It accepts that one. It become a reduced form. The potential E developed at the indicator electrode at 25 degrees centigrade, you already knew about from the Nash relationship. By using these two, the standard electrode potential developed on that at the indicator electrode, then you are going to get the form of the relations there by substituting that one. And also we have one by equation combining and equations, we have to get an equation 3 here. At equivalence point, you must know that whatever the oxidized or reduced which is equal to those 6 moles of dichromate, and here is the equations 3 here. Therefore it will be a rearrange that one. Then in the equation 4, look at that, when you rearrange that one, it becomes equation 4. Now at the equivalence point, you know that is Fe2 plus is equal to 6 moles of that one. Fe3 plus become its oxidized form of, that will be oxidized, which is equal to 3 moles of chromium ion, 3 plus ion. So substituting this one in this equations, you have to get the EMF of the cell is equal to 7EL, which is equal to 8.75 minus 0.05 log of, that will be in the oxidized to the reduced state. By knowing that equation 3, you are going to measure the what is the EMF of that particular cell. So this is the experimental procedure here. So this kind of the titration may be obtained by detecting the higher content. You know that higher content of the solutions by titration is a standard potential dichromate solution. So chemical required, you know that is 0.02 potassium molar dichromate solution, that will be a known one. Then equal volume of 0.1 molar ammonium iron sulfate solution. The latter must contain sufficient dilute sulfuric acid to produce a clear solution. So you make it an acidic in that. Using a bright platinum electrode, which is acts as an indicator electrode, and the Calomel electrode has a reference electron. Join these electrode to the circuit using a measuring EMF of the cell by using potentiometer. Set the stirrer in the mode. Proceed with the titration by adding 0.2 ml of dichromate solution to the titre. After each addition of the dichromate solution, the EMF of the cell is noted by using the table 1, that is whatever I have given a previously slide, and that is determine the endpoint by using any one of the that is the by using table and the paternal curve to determination of the end point as shown from the previous experiment. Next we go for the precipitation reactions in that potassium chloride versus silver nitrate. Here it is also we are going to use it as an indicator electrode as a silver electrode it is. Here, if an electrode reversible with a reactant dipped into solution, its potential will varying during the titration. Hence, the precipitation titrations can be carried out potentiometrically. So, here consider the changes in the ion concentration which occur during the titration of 100 ml of 0.1 molar potassium chloride with the 0.1 molar silver nitrate, so that the solubility of the AgCl, that is silver chloride, is equal to 1.2 into 10 to the power of minus 10. So we already know that is the precipitation reaction. Silver nitrate react with KCl. So AgCl as a precipitate is there. So if you construct the cell like that, that is in a, you know that it is in a calomel electrode and it is in a silver electrode. So whatever that is the absorbance of, we observe the EMF of this cell, E minus ER. E is in a silver electrode, and that is the potential developed at the silver electrode, and minus that will be a reference electrode it is there. So we are going by using a Nernst relationship, you have to write down minus ER. Then we know that by the observe at 25 degree, he observed that one that will be 0.798 plus 0.059, that is a E standard at silver. 0.0 log of Ag plus minus 2415 here. So whatever that will be there, that is E absorbance, that will be E observed the EMF of that one, which is good 0.5565 plus 0.59 log of this one. This is the indicator electrode is reversible with chloride ion. Therefore, that is the AgCl, EMF of AgCl, which is equal to standard of that one, chloride ion, plus 0.0. We can change that Ag to Cl minus because of that's whatever that is the indicator electrode EMF of that one, it is which is depending on the concentration of the chloride ion. So the concentration of the chloride ion, we already knew about that in the previous session, how the silver electrode and also that is the calculations of the EMF of that standard reference electrode. Sorry, that is the silver electrode, how we are going to use it as that one, and also construction and EMF of the cell, how we are going to calculate it by silver chloride. So from that, that is whatever that is by knowing that is the concentration of the chloride ion at 25 degrees centigrade, then from that relationship, so you are going to get 1.24. We substituted that into equation 1, then you are going to calculate the EMF of that particular cell. So this concept, okay, then operators here, that is how we are going to construction operators. So we need a silver electrode, calomel electrode, potentiometers and accessory beaker, burette and stirrer, etc. Here that is you have to take a 10 ml of potassium chloride of unknown, that is a known concentration solution in the titration vessel. So titration vessel and dilute about 100 ml with distilled water. Place a silver electrode and calomel electrode dipping into the beaker and connect to the potentiometer with respective value of electrode potential. It is there. One would normally expect silver electrode to be positive, electrode of the cell, and calomel that will be a negative, and fit a 10 ml that is a micro burette with a capillary tube extension and fill with the silver nitrate solution of unknown concentration. So then whatever you are observed during the titration, you have to change in the EMF that should be noted uh, by using a table 1. Plot E observed against the volume to the titration and find the point of inflection. You know that that's a point of inflection. It is there. Next we go for the complexometric titration. Then this is also we can use it for the determination of the endpoint of the titration here, that is the zinc sulfate versus potassium ferricyanide. Here that is here take a solutions which containing both the ferrocyanide and also ferricyanide ion. It will show a redox potential on a bright platinum electrode, because here we have to add both redox and reduced in that, because of zinc sulfate is in a salt, it will be a neutral or slightly acidic one. So in that will be reduces it oxidizes any one of that is iron, that is Fe2 to Fe3, but it is already potassium ferricyanide is already in the oxidizer form. Because of this oxidation, potassium ferrous compound corresponding to ferric salts in the presence of two moieties in solution constitute a redox system whose you know that was potential that will be given by the equation by using a Nernst relationship. That's why you are going to use the both ferrocyanide and also ferricyanide in that. Containing both the solution in analyte solution, it will show a redox potential on the indicator electrode. Usually indicator electrode we are taken as a platinum electrode. This potential will suffer change on adding the zinc ion, which remove a ferrous ferrocyanide ion from the solution. The change in potential will be very rapid as the end point of the titration that will be approaches. The reduction electrode potential for the ferric ferrous ion system. That's why you are going to develop a redox system at the indicator electrode by adding both the ferrous and the ferric, because of due to a whatever that is there, you are titrate and titrant that will be a zinc sulfate. That's why. So that will be at indicator, that will be a EMF of that system, that is the E is equal to E standard is equal to, that is a Nernst relationship that will be in the ferrous to ferric state. That will be, that is whatever that is indicator electrode, that will be potential that is measured with respect to standard calomel electrode. Then E cell of whole system that will be, which is equal to E standard minus 0.0 log of, that will be a reduced over oxidized state minus, that is the a difference of, that is SCC means standard calomel electrode. After the end point, the added zinc ion and that is only a oxidized ion remains in the solution without any reactions from the end point. You know that how that will be utilized, that all the ferrous that will be converted into ferric ions. At the end point there is no ferrous to that will be oxidized to ferric state. Therefore there is only zinc and ferric state of that will be present in that. We can find the volumes of potassium ferrocyanide and zinc plus ion reacting with the initial moves of ferrocyanide ions, and hence the composition of complex that will be going on reactions is, that is a zinc, how it will be forming complexes in that. Since the precipitate is always a neutral substance, it will have a composition of this thing. So procedure, here you take it 20 ml of 0.1 molar potassium ferrocyanide in 1 molar of HCl. That's why I'm going to explain. Before that, that is, you have to add in a HCl here and add to it nearly 1.2 ml of dilute potassium ferricyanide. We have to create the redox system at the bright platinum electrode. Then only you are going to measure the potential of developed at the indicator electrode. Set up a cell by dipping platinum and calomel electrode in a beaker and measure its EMF connecting to electrode as usual to the standardized potentiometer. Then titrate the ferrocyanide solution with zinc sulfate in the usual way and find the endpoint by plotting the differential curve. Any one of that paternal curve we can use it to identify the neutralization point. Calculate the number of moles of potassium ferrocyanide in the 20 ml of the solution taken and that of the zinc sulfate in the volume needed for the 20 ml of ferrocyanide solution. This is what we called as the name back titration. In that, how you are going to determine that how much of zinc sulfate required to give in a complex with that. The ratio of the moles of the latter to those of the former then must be 1:5. Table and paternal curve for the determination of the endpoint as shown from the previous experiment. Then we have to find out the neutralization point or equivalence point or requirement of the zinc sulfate to form a complex with a potassium ferricyanide. You can easily determine. These are the reference and sources for the prepare the study material and also making this video. Thank you.